In this video, we're going to extend our knowledge on dilations, and we're going to learn how to do dilations in the coordinate plane. So when we're in the coordinate plane, most of the time, dilations are going to be centered at the origin. So that's something to kind of make note of here. If it doesn't specify in a certain problem where the center of dilation is, you can assume that it's the origin because that's the most common. However, if it tells us what the center of dilation is, then we have to use that. So if we look at this first example, it says given triangle ABC. So let's go ahead and get those coordinates plotted. So A is -2, -2. B is 1, -1. Making sure we're labeling these. And C is 0, 2. We want to graph and state the coordinates of triangle A prime, B prime, C prime, the image of this triangle after a dilation centered at point O. So this is going to stand for the origin in this case, since it's not specified as any other point. We're going to assume that the O stands for the origin. And the 2 stands for the scale factor. So what this means is, if you remember, the scale factor, that tells us that we're going to take the distance from the center. So here's my center point, which is O. That distance to each pre-image point, we have to multiply by 2, or scale factor, to get to the image. So if we go ahead and do that, from the center to C, I have to go up 2 units. So I have to times that by 2. So instead of going up 2 units from the center, I'm going to go back to the center, and I'm going to double that. So it's going to be up 4 units. So 1, 2, 3, 4. So I'm just doubling that distance. That's C prime. From the center to point B, I had to go over 1, down 1, so double that. So instead of going over 1, down 1, go over 2, down 2. And that's going to be B prime. And then from the center to A was over 2, down 2, so double that. So over 4, so over 4, down 1, 2, 3, 4. And when you're counting, it doesn't really matter if you count vertically first, then horizontally, or vice versa, as long as you're doubling that distance in this case. And make sure that you always go back to the center when you're doubling, because remember, it's always about that center. You're expanding or contracting from that center point. So if you look at my new triangle, you can see that it was enlarged, which it should be, and it should look like it's similar to the original, so same shape, but it's twice the size. So you can kind of see that happened. You can see that these segments stayed parallel, which should also occur when we're doing a dilation. So if we go and state the coordinates, so A prime, B prime, C prime. So A is -4, or A prime is -4, -4. B prime is 2, -2. And C prime is 0, 4. So this last question says, can you find a rule that maps the pre-image onto the image without actually having to do this on a graph? So in other words, is there a shortcut? So if you compare these original coordinates to these numbers right here, is there a pattern? So if you compare A to B, or A to A prime, B to B prime, and C to C prime, is there a pattern that occurs? And hopefully you're seeing that really what we did was we multiplied each x value by 2 and each y value by 2. So that's the shortcut. So whatever the scale factor is, if you just take your x and y values and you multiply each of those by the scale factor, that will give you the dilation. However, the caution to this is it only works when you're at the origin, because you're starting at 0. So those distances that you're counting is really the same thing as the x and y value. So that's why it only works when it's at the origin. So let's make a note of that. So when dilation is centered at the origin, multiply x and y values by scale factor. So you multiply each, the x and the y value, or the coordinate, by whatever the scale factor is. And again, only when it's centered at the origin. So you might want to highlight that because that could be a common misconception that you just get in the habit of multiplying, and it's only if it's centered at the origin. So let's look at another example. This one's a little bit different because now we're looking at a line. So the first thing I want to do is I want to go ahead and graph this because we want to dilate this line using a scale factor of 3/2, and it's going to be centered at the origin, and in the end, we're going to write the equation of our new line. Now you might be thinking a line goes on forever, so how is that going to get bigger or smaller? And the answer to that is, well, the line itself won't get any bigger or smaller when you do a dilation because it's a line, it goes on forever. So in that sense, you're not going to see a difference in the length of it because it goes on forever, but you are going to see something happen with the location, with how it matches up with the center. So let's go ahead, start by graphing. So we have y equals 2x minus 4. You can decide, you can plot a table of values, get that line graphed. I'm just going to use the slope and the y-intercept. So my y-intercept's -4, so I'm going to start down at -4. So 1, 2, 3, 4. And then my slope's 2 over 1, so up 2 over 1. And just extend this all the way through the graph. And go ahead and connect these with your straight edge. And I'm going to label, so I have y equals 2x minus 4. So my center is at the origin, so let's get that plotted. So there's the center. I'm just going to put a C by that for center. And my scale factor is 3/2. So there's a couple different ways that you can go about this. But the most important thing is to realize you don't have to dilate every single point on the line. You only need to dilate either 1 or 2 points. So if you think about when we did the triangle, we dilated all 3 points so that we can connect. We dilated all 3 vertices so we could connect them. But for a line, you don't want to dilate every single point because there's infinitely many points. So if you have a minimum of 1 point, you could use the slope of the line to figure out the rest. But before we do that, we have to talk a little bit about the slopes of the lines. So what I'm going to do is I'm going to dilate 2 points, because if you dilate any 2 points, that'll always allow you to connect a line. So I'm going to pick 2 easy points, one of them being the y-intercept and one of them being the x-intercept. The reason why I picked those was only because they both have zeros in them, so they're easier to deal with mathematically. Otherwise, it doesn't make any difference. So if I look at this point and I look at this point, I'm going to go ahead and I'm going to dilate that. So if I go from the center to here, so I had to count down 1, 2, 3, 4. So that means that distance, so I'm going to kind of write this out because we're using a fraction, so sometimes that gets confusing. So we're going to take that distance down 4, and we're going to multiply that distance from the origin by 3/2, our scale factor. So if you multiply this out, this ends up giving you 6. So that means you're going to go down 6 for your new line. So from here, you're going to go down 1, 2, 3, 4, 5, 6. So there's your new point. We're going to do the same thing over here. We went over 2. So we went over 2. Multiply that by 3/2. So that gives you 3. So that means you go back to the center, just like we did in that triangle picture. Back to the center, 1, 2, 3. There's my new point. So now if you go to connect those, that gives you your new line. And now you have to write the equation of this new line. So to write the equation of this new line, you have to know the y-intercept, which that's why we purposely picked this y-intercept, and we have to know the slope. So the slope, you should be looking at these and thinking, man, they look parallel. So if you actually counted the slope, just to verify, you have 1, 2, 3, 4, 5, 6 over 1, 2, 3. So up 6 over 3, 6 divided by 3 is 2. So they are parallel. So the slopes are the same. So that means when I go to write my equation, it's going to be y equals, because it's going to have the same slope, And then my y-intercept is down here at 6. So my equation is going to be 2x minus 6. So that's one way to be able to solve this. We'll talk a little bit more about this in class, where you don't necessarily need to know 2 points, but we'll talk a little bit more about the lines being parallel and all of that. But one thing I want to point out before we move on to the next problem is instead of doing the distance counting like what I did from the center, you could have, since this was centered at the origin, I could have just taken these coordinates and multiplied them by the scale factor and got my new coordinates. That would have worked as well. So just kind of keep that in mind. Instead of doing it graphically, you could have actually written the coordinates, multiplied those by 3/2, like what we did up top, that new rule that we saw. The only caution of that is when it's not centered at the origin, it doesn't work. So that's why I wanted to show you this way. So we'll discuss this a little bit further in class, because dilations of lines are a little bit trickier. So we'll go further with that. But before I leave you, let's look at this last example where you see a dilation that is not centered at the origin, just so you can see kind of the similarities and the differences. So we're going to start off with this rectangle. So we have -2, -2. So making sure we're labeling our points. So -2, 4. F is 2, 4. Oops, I gotta fix this E. I went -2, 2, -2, 1, 2, 3, 4, and then 2, 4, and then 2, -2. So here's my rectangle. And our center of dilation is at point D. So I'm just going to mark that. And our scale factor is 1/2. So we should see a new rectangle that's smaller. But remember, everything's getting measured from D. So in this case, since it's centered at point D, which is not the origin, you cannot multiply each of these by the scale factor. And you'll see in the end kind of why that happens. So if we start at point D, what happens with point D, since it is the center of dilation, it's just going to stay in place. There's nowhere for it to go. If we go to E, we had to go up 1, 2, 3, 4, 5, 6. So instead of going up 6, well, we're going to go half of that. So go up 3. So go back to the center, and we're staying on that same line. So we're going to go up 1, 2, 3. There's E prime. To get to G was over 1, 2, 3, 4. So cut that in half. So instead of 4, you're going to go over 2 on that same line. So over 2. And then F, again, we're staying on that same line, but really if we just count up and over, it'll do the same thing. So it's up 6 and over 4. So we're going to cut that in half. So up 3 over 2, and that gets us F prime. So here's our rectangle. It should look like it got half as big. And you see that D stayed in place. So I'll just write D prime in the same place. So let's go ahead and list out our coordinates. So D prime, E prime, F prime, and G prime. So D prime stayed in the exact same spot. E prime became -2, 1. F prime became 0, 1. And G prime became 0, -2. So just to, again, to point out the fact that since this was not centered at the origin, look at the connection between these coordinates and these. It doesn't appear that there is a connection. You couldn't just multiply the originals by 1/2 and get these. So again, that's because the center of dilation was not at the origin, so everything was shifted. So those distances weren't the same as the coordinates. So that's why it doesn't work. So in the end, you have to do ones like these graphically. Whenever the center of dilation is not at the origin, you just do them on the graph. So it's good to know the graphical way, but knowing the algebraic shortcut rule is helpful for something that's centered at the origin. Also a great way to check your work. So go ahead and try check your understanding problems, and we will discuss some more dilations tomorrow in class.